Hello, and this is Kristen from FREEDM Systems Center of North Carolina State University. Today we will show you a microgrid resynchronization algorithm implemented on the Resilient Information Architecture Platform for Smart Grid, also known as RIAPS. This project is supported by ARPA-E and is coordinated with Vanderbilt University and Washington State University. Shown in the figure is a microgrid with 4 distributed generations. Each of them can be power electronics interfaced renewable energy sources such as PV or batteries. On each of the distributed generations and other elements in the microgrid, a RIAPS node is deployed. Each RIAPS node has local sensing, actuation, computing, and communication capability. What RIAPS provides is a software layer that isolates the hardware details so that the software application will be portable across multiple devices. Some other unique services offered by RIAPS include real-time data dissemination, fault tolerance, and coordination across apps distributed over the network. RIAPS brings distributed intelligence to the smart grid. This is realized through software apps running on embedded computers attached to the nodes of the power system. It provides the technological foundation for distributed and resilient apps for improved and effective energy management. The example application in this video is a distributed control for microgrid synchronization implemented on RIAPS. The app has 2 components, voltage and frequency restoration and microgrid synchronization. First, let's look at the control algorithm. With droop control acting as primary control for the distributed generations, frequency and voltage deviation will be induced when the microgrid is islanded. A distributed secondary algorithm in the yellow box is used to restore the frequency to 60 Hz. If the microgrid needs to synchronize with the main grid, another term, shown in the green circle, is added. This term will drive the microgrid frequency to eliminate the phase angle between the microgrid and grid. Likewise, the voltage magnitude of the microgrid is also restored to its nominal value by secondary control. After the control algorithm, let's have a look at the hardware platform for testing the application. As you can see at the bottom of the page, there are 4 key components. The first component is the Opal-RT real-time simulator in which the power system model and inverter switching model are implemented. The inverter models in the Opal-RT simulator are controlled by industry-grade digital controller F28377S DSP. Each DSP is associated with a Beaglebone Black single-board computer, which is the hardware for the RIAPS node. As the last component, a remote Linux machine can collect and store data. It also can display data in real time. With such a hardware platform, we can achieve close-to-reality simulations and verify the control algorithm performance with real-life issues. For example, implementing the primary control on the DSP helps us study measurement noise and sampling effects of the digital controllers. The inverter is simulated in the FPGA solver of the Opal-RT. The time step is 0.5 microseconds. The DSP can communicate with its RIAPS nodes using the Modbus protocol. The secondary and resynchronization control algorithm introduced before are running on the RIAPS nodes. Now let's start the demo. The upper right window is the RIAPS Linux machine. With RIAPS, we can distribute the code from a single computer to all RIAPS nodes. First, let's energize the distributed generation. The grid voltage magnitude and frequency are constant. Its phase angle is used as the reference. When connected to the grid, the microgrid has the same voltage and phase angle. This can also be seen from the scope, which shows the phase A voltage of the grid and microgrid. All the power electronics interface battery energy storage systems have 0 power command in the grid tied mode. The output of the PV inverter can be manually set to simulate different solar radiation conditions. Now we open the relay to disconnect the microgrid from the grid. In islanded mode, the microgrid has a different voltage magnitude and phase angle from the grid. The voltage waveforms are shifted from each other. All operation parameters are stored in the RIAPS data logger. Now the loads in the microgrid are supplied by the distributed generations equally. The power exchange between the microgrid and grid is 0. Next, we will enable secondary control on the RIAPS nodes to restore the microgrid voltage and frequency. The change of voltage magnitude and angle during the restoration is stored by the RIAPS data logger. Very quickly, the microgrid frequency is restored to 60 Hz by secondary control, but there is a constant phase shift between the grid and the microgrid. Due to this phase shift, we cannot reconnect the microgrid back to the main grid. To eliminate the phase shift, we will enable the synchronization control. With synchronization control, the microgrid voltage is shifted gradually to the grid voltage until the phase difference is eliminated. Now in steady state, the microgrid and grid voltages are synchronized. They have the same voltage magnitude, frequency, and phase. The microgrid can be reconnected to the grid. Finally, we connect the microgrid to the grid by closing the relay. The microgrid is now grid-tied mode again. As before, the load is supplied by the grid in grid-tied mode. The power of the battery energy system is 0.